Hello everyone. Here we are given that G is a group. It could be finite, it could be infinite, but H is a non-empty, finite subset of group G. Focus being on finiteness of the group. Okay, subset. Okay, so let H be a non-empty, finite subset of the group G, and H is having a special property that H is closed under the operation in G. Okay, now we are asked to prove that H is a subgroup of G. All right, so let G comma say dot, let dot be the operation in the group G. Okay, let G comma dot be a group. This could be finite, this could be infinite. We have no restrictions on G. Okay, now we are given that H is closed under dot. Okay, what does that mean? Take any two elements. Okay, given any elements a comma b in the set H, we have that a dot b, which I'm writing it as ab. Okay, this is in H. This is what we mean by closed. Okay, closed under the operation. So given any a comma b in H, we have that ab is in H. This is the given property. Now we are asked to prove that H is a subgroup. Okay, by the definition, when will H be a subgroup of G? We have to show that one, given any elements A and B in H, A B must be in H, right? The second property that it must satisfy is the identity element. It should be there in H, and third condition is give me any element in the set H. Given any A in H, we need that A inverse also must be there in H. Okay. Now, by the given condition, property 1 is definitely satisfied. Correct? There is nothing to prove in that. It is trivially satisfied by the given property. We have to focus on 2 and 3. Now, we will focus more on 3. Why? Because if we given that H is non-empty, right? So H is non-empty. So if there exists at least one element A in H, right? H is non-empty. So at least one element is there. Call it A. Okay, let A be there in H. If we show that A inverse is also in H, then by the given property, their product A in A dot A inverse, right? That also, what is this? This is identity. This also must be in H by given property. Correct. So, by the given property, give me any two elements in H, their product AB will also be in H. So, if we show that A is in H and A inverse is also in H, then A dot A inverse, which is nothing but identity element, it also must be there in H by given property. Okay. So, if we prove 3, then 2 will follow. Correct. So, our focus will be on 3. Okay. So, given H is non-empty. Okay, now so H will have some element, call it A. Let A be in H. Now this A, this element could be the identity element in G, it could be non-identity element in G, right? Because we know that H is a subset of G. So whatever element is there in H, it is actually an element in G. Okay, now this A that is given to be in H, it could be identity element, it could be non-identity element. So case 1, A is equal to the identity element in the group. In this case, what is A inverse? That will be again identity element, right? Because in the group G, A is an element in the group G. In group G, A inverse exists, right? And that A inverse will be identity inverse, which is nothing but identity. Correct. Now this in G. Okay, now this identity element is actually equal to A and it is given to be in H. So if the A is equal to E, then trivially A inverse will also be in H. Okay, in this case, so in the case 1, when A is equal to identity element, its inverse, which is again identity element, is present in H. Okay, in this case we are done. Now case 2, A is not equal to identity. Okay, this is the second case. All right. Now, so far we have not used the finiteness of H. Okay, it is in this case that we will use the finiteness. All right. So, to use the finiteness, what will we do? Our idea is we will consider a power 1, a square. What is a square? It is nothing but a dot a. Okay, a square. We will consider a cube, a power 4, etc. Okay, all such powers of a. Okay, we will consider this. Consider this. Okay, we will consider these. Now we know that a is in H, correct? So a dot a must also be there in H by the given property, correct? Right? So a square is there in a square is there in H, correct? Now, similarly, we have now that a is there in H, a square is also there in H. So we will have that a square into a, which is nothing but a cube. This also must be there in H, correct? So following like this, any a power n will be there in H, where n is a natural number. Natural number means n has to be equal to 1, 2, 3, like that, correct? So any a power n must be there in H by this argument. Okay, so we will note that down. Now, uh, here we have that a power 1, a power 2, a power 3, etc. It looks like a very big list. It looks like an infinite list, right? But can it be infinite? No, right? All of them must be in H, right? So a square, a cube, etc. Everything must be in H. But H is finite. H is finite, right? So how can a set which looks like infinite be here? It cannot be, right? So the thing is, after some point, it has to repeat. That is, say for example, a square, a cube, a power 4 are all distinct. Okay, this is just an example. Now, a power 5 will be one of them, something like that. Okay, a power 5 has to be uh, a power 6 will be a square and things like that. Okay, if it is going like this, then it is just the same four elements which just keep on repeating, right? So what will we have? A power 7 will be a cube, a power 8 will be this, and then a power 9 again will come back to a, and things like that. So there must be this kind of repetition. Okay, there must be this repetition. Now suppose there is no repetition. If a square, a cube, etc., everything is distinct. Okay, if all of them are distinct, then all of them are definitely contained inside H. Okay, so H will have to be infinite, right? So the argument is, if a a square, a cube, etc., are all distinct, then we know that this set a square, a cube, etc., this is going to be an infinite list. Okay, it is going to be an infinite set, and this will be contained inside a finite. This will be contained in H, but H is finite. Okay, so you see the contradiction, right? How can an infinite set be sitting inside a finite set? It cannot. Okay, so this a square, a cube, etc., all of them cannot be distinct. So after some point of time, the pattern has to repeat. Okay, so there exists, say, some j which is not equal to I, and say j is strictly greater than I. We can take like this, right? Because if we are taking I to be 2 or 3 or something, and j to be a very big number, such that a power j equal to a power I. Okay, this has to be there. We said that there has to be repetition. So some smaller number, say for example a power 10, it has to be equal to some bigger thing, a power some bigger number, correct? So we will take I to be the smaller one, j to be the bigger one. Okay, so j and I are not equal, and j is strictly greater than I, but we have a power j will be equal to a power I. Okay, this must happen, right? Because of the finiteness of h. That is where the importance of h being finite comes in. Okay, now we know that a power j and a power I, these are in h. I agree. Now h is a subset of g, correct? So this a power j and a power I, these must be elements of g as well, correct? So these a power j and a power I are actually elements of a group. Okay, so we can actually talk about a power I, the whole inverse. Okay, this is actually equal to a power minus I. Okay, this actually exists, correct? But where does this exist? In G. In the group G, a power minus I will exist. Okay, so now instead of talking about H, we will talk about a power J and a power I in G. Okay, so we will have that a power J comma a power I are in G. So it makes sense to talk about a power minus I. Okay, in G we will have this. So we will have a power j into a power minus I, which is actually equal to a power j minus I. Okay, but what will be this? This will be equal to identity, right? Because a power j equal to a power I, we can multiply by a inverse on both sides. So we'll have a power j into a power I minus I, which is equal to a power I into a power minus I, which is actually equal to identity, correct? So we'll have that a power j minus I is actually equal to identity. Okay, now this, we know that j is strictly greater than I. So j can be equal to I plus 1 or it can be more. Okay, so j minus I will be equal to 1, or it will be 1 or 2 or 3 or something like that. Okay, it has to be one of them. Can j minus I be equal to 1? Is this possible? Suppose this is possible, then we will have that a power j minus I is equal to a power 1, but that is equal to identity. Okay, what that will mean that a has to be identity, correct? Because we know that a power j minus I, this is identity, but j minus I is 1, then a power j minus I is equal to a power 1, that has to be equal to identity. That will mean that a has to be identity, but this is a contradiction, right? Because we began with the case of a not equal to I. So this is not possible. This is not possible. So j minus I cannot be equal to 1. So j minus I must be strictly greater than 1. Okay, so j minus I must be strictly greater than 1. So j minus I must be some of the like, it must be one of 2 or 3 or 4 or something like that. Okay, so we will have that j minus I is strictly greater than 1. So j minus I minus 1 will be strictly greater than 0. Okay, so we will have that j minus I minus 1 will be a natural number, correct? Because j minus I is like 2 or 3 or 4 or something like that. So j minus I minus 1 will be 1 or 2 or 3 or something like that. So j minus I minus 1 must be a natural number. Okay, we note this. Now a power j minus I, we can write this as a power 1 into a power j minus I minus 1, same thing. Okay, now, but what is this? This is actually identity, correct? The E is actually equal to a power j minus I is equal to a power 1 into a power j minus I minus 1. Okay, so what does this mean? This means that a power j minus I minus 1 is the inverse of a, correct? This means that a power j minus a power j minus I minus 1 must be an inverse of a, correct? Now, we had noted that any a power n is in H where n is a natural number. We had noted this here, right? Where is it? Okay. Yeah, we had noted this here, right? So any a power natural number must be there in H. So in particular, a power j minus I minus 1 must also be in H. Correct? But what is this? This is actually a power minus 1 is in H, because this is the this is inverse, right? So a power j minus I minus 1 must be equal to a inverse. Okay, so a inverse must be in H. Correct? So we started with a is in H, and what did we get? We got that a inverse is also in H. This is true for any a. It's true for all a. Correct? So aren't we done? Because uh, here we started with a non-identity element and we got that a inverse is in H. So aren't we done? The property 3 is satisfied, right? Because take any element in H, it can either be identity element of the group G or it is not the identity element of the group G. If it is the identity element of group G, we are done. Now, if it is not the identity element of the group G, still we proved that A inverse must be there in H. So, in any case, if A is in H, A inverse must be in H. So, property 3 is satisfied. So, consequently, property 2 is also satisfied, right? So, all the conditions for H being a subgroup is satisfied. So, H is a subgroup of